effect of change in concentrations, or the other words, effect of dilutions on conductance of electrolytic solutions, response of conductivity and molar conductivity to change in concentration of electrolyte, as we know, weak electrolytes does not ionize completely in aqueous solutions to give us complete ionization, and that's why their conductivity is smaller compared to strong electrolyte that ionizes completely. So here we having a HCl, which is completely ionized, all are into its ionic forms, while acetic acid, which is a weak electrolyte, you saw there, their conductivity is poor, and we saw here many unionized acetic acid molecules and few ionized acetic acids. So conductivity of solution is only because of ionized ions. Now first, effect of dilution on conductivity. Conductivity always decreases with decrease in concentration for both weak and strong electrolytes. The reason is, we know when we dilute it, the number of ions per unit volume that solution can carry a current reduces on dilution. So basically per unit volume, number of ions present for conductance will reduce. That is the reason conductivity will always reduce with volume increase or dilution enhancement. We added a volume here. What happens? Conductivity will go down. So conductivity we know is equal to conductance into cell constant, which is per meter. And conductivity will go down. Conductance will go down. That's why conductivity will go down. Now, in the effect of dilution on molar conductivity, you will be surprised that molar conductivity will increase with decrease in concentration. It may be a surprising. Why molar conductivity increases while conductivity reduces with dilution? The reason is, conductivity reduces with concentration, but in case of molar conductivity, the reduction in conductivity is overcome by falling concentration, which is in denominator in a molar conductivity expression. You see, here it is at the bottom, here is molarity. When concentration reduces, this also reduces, but reduction in molarity is faster, or it will overtake the conductivity because this denominator, so overall effect will be solution molar conductivity will increase. We want to understand it from a concept point of view. What happens when solutions are concentrated? There is the effect of ions on each other's conductance. They interfere, they keep on striking each other. Their movement is not free because of their interactions. So they slow down each other. But when we dilute it, number of ions per unit volume reduces. So each ion can move better. Because of their better movements, conductivity or the molar conductivity will increase. So molar conductivity basically takes about the movement of ions, while conductance will take about in totality movement of ions. That is the reason when we talk about molar conductance, movement of individual ions is more important than the collective behavior. That is the reason. Because they are able to contribute better on a dilute concentrations. They perform better. Molar conductivity increases on low concentrations. For weak electrolytes, if we plot molar conductance versus under root of concentration, this is for strong electrolytes, but we get a straight line, which C means the molar conductance enhances with dilution or reduction in concentration. So it's easy for us to extrapolate. If we say at a zero concentration or at a infinite dilution where concentrations are negligible, we get this limiting concentration or limiting molarity. Same thing for weak electrolytes. There is not much significant enhancement in their conductance, molar conductance at low concentration, but at a very low concentrations, when we go down further, there is asymptotic increase in the molar conductivity of weak electrolytes. When concentration approaches to mathematically zero, the molar conductivity is known as limiting molar conductivity and represented by symbol EM0. This is a symbol for limiting molar conductivity of. So here we see this is for strong electrolytes. Because of this straight line, we can extrapolate it at to infinite low concentrations. But for weak electrolytes, this extrapolation is not possible. That's what we see. When C approaches to zero, the molar conductivity approaches to limiting molar conductivity. Now, what are the problem we saw for weak electrolytes? That we can't measure their limiting molar conductivity at zero concentrations. That problem to great extent was answered by law known as Kohlrausch law. Now let's see what is Kohlrausch law say. Kohlrausch law of independent migration of ions state at infinite dilution, anions and cations of electrolyte individually and independently contribute to the limiting molar conductivity of an electrolyte. Try to understand it again. At infinite dilution means at the limiting concentrations, when the concentration is nearly zero, we can't, it is mathematically approaching zero. At this very low concentrations of electrolytes, anions and cations, both of electrolyte, will individually, mean in themselves, and independently, mean independent of the other cations and anions present, they contribute to the limiting molar conductivity of electrolyte. The beauty of the Kohlrausch law is we can combine any ion at dilute concentrations and find the molar conductivity at that temperature. So we doesn't have to depend upon the sodium because they are independently contributing individually and independently. So sodium, let's say sodium ion is present in sodium acetate or sodium chloride, or it is a soda amide. Anywhere sodium is present, or potassium chloride or potassium acetate, anything. Potassium will contribute independently, sodium will contribute independently. Ammonium nitrate or ammonium chloride, ammonium ion contribution will be independent of its salt. That's the beauty of Kohlrausch law. Every ion contributes independently. That's what we have. These are the limiting molar conductivity of individual ions. Like proton, we have 349.6, sodium, potassium, calcium, magnesium. You see here the same reason that molar or limiting molar conductivity here is 50 for sodium, potassium is at 73, magnesium is 16 and calcium 190. The reason is the same as we discussed earlier. Hydrated shell of smaller ions is bigger compared to larger ions. Calcium having a smaller hydrated shell compared to magnesium. Potassium have a smaller hydrated shell compared to sodium. That's why its mobility of potassium and calcium will be better than sodium and magnesium. So we can use these ions independently to calculate any salt. Let's find magnesium dichloride's molar conductivity. It will be 106 plus 2 into 76.3 because 2 chlorides are present. Total conductivity of magnesium chloride molar conductivity will be 258.6 Siemens per centimeter square per mole. Simple mathematical expression. The difference of limiting molar conductivity of alkaline ionic compounds such as electrolyte sodium X and potassium X or any X is constant. Here we see chloride are same, only potassium minus sodium is equal to potassium minus sodium for bromide also. Iodide also is different, so it's almost constant because difference is only between potassium and sodium, which is 23.4. If we subtract potassium minus here is 23.4 only, same. So it explains how we can use individual ions to calculate the total conductivity of particular electrolyte. Similarly, difference in the molar conductivity, which is limiting molar conductivity of ionic compounds with the same alkaline atom but different halides, such as electrolytes MCl and MBr for any M is constant. That's what we saw. If we keep these cations same, we vary the anions, same results we'll get. That's what the Kohlrausch law say. Individually and independently, every ion contributes independently and this contribution will remain the same irrespective of its salt. It can be a potassium salt or it can be sodium salt. So the generalized form of Kohlrausch law is limiting molar conductivity is equal to a coefficients into molar conductivity of cation, coefficients molar conductivity, limiting molar conductivity of anion, which are coefficients in a molecule. Now we see the application. We just saw in that molar conductivity versus over square root concentration plot. For weak electrolytes, extrapolation is not possible like for strong electrolytes because it was linear for strong electrolytes but asymptotic for weak electrolytes. So how to find the limiting molar conductivity of weak electrolytes? That is by using their salts like sodium acetate, sodium chloride and HCl. If we will write the ionic equation for acetic acid, it will be sodium acetate plus HCl minus sodium chloride. These all are strong salts having a better dissociation than acetic acid, and we know the linear plots for all of these. That's what we saw. The limiting molar conductivity enhances dramatically or asymptotically. This is called asymptotic, which never meets the axis but keeps on going parallel to it. So it's limiting molar conductivity for weak electrolytes we can't determine experimentally by extrapolation. And they having the degree of dissociation is small. We can calculate the degree of dissociation by taking a ratio of molar conductance of electrolyte at particular concentration by taking the with limiting molar conductivity of the same electrolyte. Now, using the same mathematical expression of Kohlrausch law, we can calculate the molar conductance of limiting molar conductance of weak electrolytes. Here it's a acetic acid, which will be HCl plus sodium acetate minus sodium chloride. We are getting a here limiting molar conductivity of acetic acid that can be substituted here, and remember, it can't be determined experimentally. We have determined it indirectly using the limiting molar conductivity of other strong salts, and this obviously we can find it out at any concentration. By taking this ratio, we get the degree of dissociation. It is just like that. This will give the total ions concentration. This is because of only the ions present at a particular concentration. So the ratio will be gives us a fraction of ions that are present here is the acetate ion. So we substitute, this is a dissociation constant for equilibrium, C alpha 1 minus alpha. Substituting the value here, we get limiting molar conductance for a particular concentration at a concentration C. Then this is a limiting molar conductivity of electrolyte, and which is the difference between limiting molar conductivity minus molar conductivity. Reaction constant can be calculated from the degree of dissociation. So this is the way we can calculate our dissociation constant as well as degree of dissociation first, then dissociation constant from it. So that's why we told very beginning, in analytical chemistry, these conductivity measurements having a huge role. Electrolytic cells and electrolysis. In electrochemical cell, we utilize the chemical energy that drives the electrons in outer circuit, and in electrolytic cell, we supply electrons externally that drives the chemical reaction in the cell. Like here we have applied a voltage across a electrolytic cell, negatively charged cathode and positively charged anode. In this electrolytic cell, on applying a voltage, you see the ions start moving towards their respective counter electrodes. Positive will go to negative, negative will go to positively charged electrodes.